Okay, so I guess we can start. Good evening, everyone. So today we have a pleasure to have a talk by Professor Luc Postle, who is, thank you for shushing, who is a renowned expert in graph theory and received several prizes for the studies in the graph theory, such as Canada Research Chair, Early Researcher Award of Ontario, and I believe recently Coxeter James Prize. And today we will listen to the talk on hypergraph matchings, avoiding forbidden submatchings.
Thank you everyone for coming. So today I'll be talking about hypergraph matchings, avoiding forbidden submatchings. So we'll learn what that's about when we get to it. I should mention that all of this is joint work with Michelle Delcourt, who's in the audience here. Let's get to it. So I'm going to start my talk by talking about two different problems that are of interest to me. And we'll start with the first one, which is in design theory. It's about high-girth designs. So what is this? Let me first tell you about designs. So let n, at least q, at least r greater than or equal to be integers. So you might have heard of Steiner systems. Let me define a partial Steiner system. A partial NQR Steiner system is a set S of Q subsets of an N set V, such that every R subset of V is contained in at most one Q set in S. Now you might more have heard of a Steiner system, which is the same definition, but with the words at most one replaced with exactly. So this is one of the central objects in design theory, this highly symmetric object where you want every R subset to be in exactly one Q set. So you want to do this partition. And a natural question about designs is, for what n, q, and r does there exist an NQR Steiner system? So when can we build this object? And it turns out that there are obvious necessary divisibility conditions. So namely, if you think about how the sets would have to go, you require the following conditions: that q minus I choose r minus I has to divide n minus I choose r minus I for all I from 0 up to r minus 1. Because you can sort of count how the degrees or the number that goes into these q sets and realize that you would need this set of conditions. By thinking about how an I set would have to live inside the object, you get these obvious conditions. And so we'll say n is admissible if it satisfies these properties. And then there was the notorious conjecture from the mid-1800s, this existence conjecture for combinatorial designs. And it suggested that for sufficiently large n, so let's get rid of small counterexamples, maybe it doesn't work for small n, that there exists an NQR Steiner system whenever n is admissible. So these obvious necessary divisibility conditions, they should be sufficient. And this is a very nice conjecture. It's just, it's about set theory. Can we build these highly symmetric objects? So this started again in the 1800s from work of Kirkman and from Steiner and onward until they sort of formulated this idea. And so what is known about the history is, let's just start with this one. So yeah, Kirkman actually did this in 1847, so he proved that Steiner triple systems exist. He actually did it before really Steiner came along, and so there's a bit of a misnomer. They really should be called Kirkman systems, but this is the fate of history. So Kirkman did this in the 1840s. Then work was done on smaller numbers. The real big breakthrough was by Wilson in 1970s, who showed the R equal 2 case. So more than 100 years later, we finally resolved the R equal 2 case, which is, as you'll see in a bit, the graph case. But this is really a hypergraph question for general uniformities. And so not really much was known. Some work was done on 3 and 4, but we didn't even know designs exist really for infinitely many n for larger values of R, say R at least 6. But what was known was the approximate version was proved by Rodel in 1985. This was the Erdo-Shihani conjecture. Erdo-Shihani said this thing is too hard in the 1960s. Can anyone prove the approximate version? And what do I mean by approximate? That you can get almost all the sets. Like you can cover almost all of it. It's not a perfect decomposition, but almost all. And he invented a celebrated nibble method I'll talk about a little bit later to resolve this. So we knew approximate ones work for all Q and R, and then you don't even need divisibility. And finally, the full conjecture was proved by Kivosh in 2014. So nearly 150 years later from when it was first thought of, finally we resolved this big conjecture in the middle of design theory. And he did it using a method he introduced called randomized algebraic constructions. The full conjecture was also then, a second proof was found by Glock-Kuhn, Low, and Ostis. So Kivosh has had some algebra with it. They found a purely combinatorial proof using the method of iterative absorption. And both of these have had influences now in design theory. So this was a monumental achievement that we could finally prove this existence conjecture. So then what, right? It's mathematics. We just stop, right? We've proved the big conjecture. There's nothing more to do. No, we don't stop. Let's keep going. So let's talk about high girth designs. So what is that? Well, in a partial NQR Steiner system, I'll define a JI configuration as a set of IQ subsets that span at most J elements, or J vertices, if you want to think the elements are vertices. So this is just some notation for sort of how dense they are, like this JI configuration. And an interesting observation by Erdős about Steiner triple systems was that they always contain an I plus 3 I configuration for every fixed I. So that's kind of easy to see. You contain a 4-1 configuration. That would be a triangle or a 3 set on at most 4 elements. Actually, you contain a 3-1 because you contain a triangle. 4-1's nice because then you're missing one of the pairs being covered. So if you're in a full Steiner system, that pair must be covered. And you can add one more vertex and one more vertex. And you can keep doing this. So it's a rather simple observation that, okay, they have to contain these things. And then Erdős asked, what about the next lowest one? What about I plus 2I? He couldn't find an obvious reason that Steiner systems had to contain these kinds of configurations. And indeed, actually, they can't have 4-2 configurations. That would be 2-3 subsets intersecting in a pair. That's precisely what it means to not be a Steiner system. And he wondered, could you exclude larger ones? And so you can define the girth of a Steiner system, sort of analogous to how you would do for graphs, but using this idea. So you could say the girth is the smallest integer k, where you contain a k plus 2k configuration. And then in that term, you can rephrase what he wanted to ask as this, and he actually conjectured it, that for all g, there is n large enough that for all admissible n larger than that ng, you can find a Steiner triple system of girth at least g. That you can find these Steiner systems of sort of arbitrarily large girth. And I think that's a really nice conjecture from the 1970s. Again, this is only about Steiner triple systems, which we already knew about in 1847. And here we're conjecturing high girth in the 70s. What's known about this conjecture? Well, here was the history. A partial Steiner system was proved to exist of quadratic order, but where the constant unfortunately went to 0. This was done by Lefman, Phelps, and Rodel in '93, so 20 years later. And then just a few years ago, the approximate version that Rodel had done for designs was done here by Bowman and Warkey, and separately and independently by Glock-Kuhn, Low, and Ostis just a few years ago was published. So it took almost 50 years to finally prove the approximate version of this Steiner triple system. But amazingly, then, building on their work and incorporating absorption, just 2 years later, the full conjecture has now been proved. So this was done by Kwan, Sasani, and Simkin just last year, and kind of sparked our interest in the topic, actually. Okay, so I've shown you yet another conjecture, long gap, finally proved. Clearly we're done there, right? No, we can keep going. We could ask about not just triple systems, but high girth in general. And the observation made by Glock-Kuhn, Low, and Ostis was similar reasoning to Erdős's observation is these Steiner systems must in general contain this number. So you can reason out, but they calculated it's q minus ri plus r plus 1i. Same argument. And so they naturally thought we should define the girth to be 1 lower. So here's the definition. It's the smallest k where you contain this set of this configuration. And they boldly made a conjecture. And so they did this. It's also independently by Kivosh and Long around the same time. And they say that for all g in sufficiently large n, again, whenever n is admissible, you should be able to find a Steiner system, an NQR Steiner system, of arbitrarily large girth. So girth at least g, right? But notice this is what I'll call the high girth existence conjecture. It is a common generalization of the existence conjecture, because you just remove the girth, and the high girth triple systems one, because that's just for 3 and 2. So it's a common generalization of these two old conjectures that only have recently been proved. So now this seems quite impossible, but we could ask, what can we do? And so here's what we can do. We can show the approximate version. So that's what we did, Michelle and I, last year. We were able to find a general argument to prove this approximate version. So generalizing Rodels, generalizing those other groups. So you can find a partial Steiner system with almost the right number, so almost covering, of girth at least g. So I thought that was quite nice. You know, there's still more work to be done, of course, to try to prove this, but it's, at least the approximate version is true. And I should mention this was also independently done, so within a month on arXiv, by Glockios, Kim, Kuhn, and Lechev, who did some of the similar things I'll be talking about in this talk. So again, stop me if there are any questions, but this is what I wanted to say about designs for now. This is the high girth existence conjecture. We can prove the approximate version. So this is the high girth designs. So that's one problem. Now let me bring in a completely different area. So I do more coloring. Let me tell you a coloring problem. This is about edge coloring. So you all probably have heard of this. So an edge coloring of graph G is assignment of colors to the edges. So adjacent edges don't receive the same color. The chromatic index, denoted chi prime of G, is the smallest integer k, such that G admits an edge coloring with k colors. And there's the famous classical theorem of Vissing, which shows that the chromatic index of a graph is at most delta of G plus 1. And you need the plus 1. And there's the obvious lower bound of the delta G, the max degree, because all the edges near a vertex would then need different colors. So we study this in our graduate graph theory class and show the proofs. What you might not know is there's another generalization, which will be relevant for later, to list coloring. So the list chromatic index, denoted chi L of G, is the smallest integer k, such that whenever you assign k colors to every edge, you can find a coloring from that. So that's called a k-list assignment. And you might not know there's another famous theorem of Kahn's from 1996 that shows that the list chromatic index is at most 1 plus little o1 delta of G. So there's this famous thing, I won't state it, but called the list coloring conjecture, which asserts that for edge coloring, list and ordinary are equal. So it's conjectured that these two numbers are equal, and then Vissings would tell you it's at most that. We don't know that, but Kahn was able to show morally they're equal. They're approximately equal. Yes?
What's hiding in the little O1 there?
So originally he just did it for O of 1. There have been more recent resentments. The best ones is by Malloy and Reed. You get an error of around square root delta with a log fourth of delta. And there's reasons we kind of can't get beyond that. So it seems very hard to improve this all the way. But it would be conjectured. That would be a special case. Okay, so that'll come back later, but I want to tell you a different problem, which I can phrase sort of as this question. In the spirit of this talk is going to talk about high girth combinatorics. Can we make the edge coloring high girth? So what would that mean? That might be silly to you, because if you look at one color class, it's a matching, and a matching has infinite girth. There are no cycles. But what you can do is look at bicolored cycles. In particular, we can say an edge coloring of a graph is acyclic if it contains no bicolored cycle. So bicolor just meaning color, two colors, 1 and 2, 1, 2, etc. So it'd have to be even. And it was natural to wonder, could we avoid this? And so you could define the acyclic chromatic index of a graph, denoted A prime of G, as the smallest integer k, such that G admits an acyclic edge coloring with k colors. And impressively, there's something called the acyclic edge coloring conjecture. This was independently raised by Fiemczyk in 1978, and Alon, Sudikoff, and Zaks in 2001. And they both conjecture that A prime of G, the acyclic number here, should be at most delta plus 2. So you might wonder why plus 2 instead of plus 1 from Vissings. It turns out it's not true for plus 1. In particular, if you look at K4 or any even clique, you can just easily do a counting argument to show you won't be able to get it to be acyclic with delta plus 1 colors. So then they conjectured, well, this is the first value we don't know. Let us again boldly conjecture that this should be true, even though really there's no reason to think it should be. So what's known about this conjecture? Well, here's the history. I'll show it. Well, can you do any bound? Well, Alon, McDermott, and Reed in 91 actually showed you could do 64 delta. Malloy and Reed in 98 improved this to 16 delta. So these were using local lemma, or lopsided low-Voss local lemma results. Nadreka, Procacci, and Scopola in 2012 did 9.62 delta minus 1. The best accepted current bound is 4 delta minus 1 by Espero and Perot in 2013 using what you might have heard of, the entropy compression method. So there was this nice method developed in tandem or in advance of the local lemma, and this is one of the hallmarks of that method is that you can get 4 delta minus 1, a pretty short proof for this acyclic edge coloring conjecture. And that's the best we know. So we're still quite far away from there. And the entropy compression method, it's thought would only get you at best to 2 delta. So we're still quite far away from this acyclic one. So what did we do? Well, you can relax the conjecture in sort of 2 ways. So here's one way, that's nice, is Kai, Perenow, Reed, and Watts in 2017 showed that if the graph itself is high girth, so for every epsilon there exists a girth g epsilon, that if you're at least that girth, so if you don't have short cycles, you can actually do it with 1 plus epsilon delta colors. So somehow, yeah, having short cycles is bad. But we know how to do it if there aren't any short cycles. So what did Michelle and I do? Well, we kind of attack it from the other side. So this high girth question. Maybe infinite girth is too much to ask for. Maybe, having this no cycles is too much to ask for. So let's call an edge coloring L acyclic if it contains no bicolored cycle of length at most L. Now, I really could have called that girth at least L edge coloring. There's just already enough girths in this talk. We didn't want to confuse you. So I'll nicely call it L acyclic to differentiate. And here's our theorem. We show that for every epsilon and L, there is a number, delta 0. If you have large enough max degree, then you can get an L acyclic edge coloring using at most 1 plus epsilon delta colors. So you can do the 1 plus little, you can prove the approximate version of the acyclic edge coloring conjecture, except you're only getting the short cycles, the short bicolored ones. So of course, this screams to you, this one we can do for high girth, this one can get rid of the short cycles. Why can't we just combine the two? Unfortunately, the issue is here. They fundamentally use the fact the graph has no short cycles, not just that you don't want to color them. So unfortunately, you can't just combine them. But if you're asking for a high girth coloring, we've done that now. So we can prove it approximately in the high girth setting. And my question then is, how are these two problems, high girth designs and acyclic edge coloring, related? All right, so I started off the talk, here's 2 nice problems. One's in coloring, one's in design theory. Sure, they both have the word high girth in them now, but that's maybe just a coincidence. Are they actually somehow fundamentally related? Are they the same? So that's what I'll try to convince you in the rest of the talk, is that these really are very similar problems that can be attacked with similar methods, in particular with a general black box theorem to imply both of ours. And to do that, we need to go to hypergraph matchings. So you might know matchings. Let's talk about hypergraph matchings. So what is a matching in a hypergraph? It's just a set of edges that are pairwise vertex disjoint. Same definition as in a graph. You just want vertex disjoint edges. And the important point is that many problems in combinatorics can be encoded as hypergraph matching, or if you're doing like more vertex coloring, hypergraph independent set problems. So it turns out you might not think this in graphs, but by allowing extra uniformity, by allowing you to pass to hypergraphs, many, many different problems can be encoded in these terms. So then coloring and matching become fundamental at the hypergraph level. So how do I convince you of that? Well, let's start with the first problem. How can we encode designs as a hypergraph matching problem. So maybe if you've seen this, if you haven't, let me explain it to you. Well, you could actually do it. How do you do it? First note that an NQR Steiner system, it sounds like it's set theory, it's graph theory. It's equivalent to the decomposition of the edges of the complete R-uniform hypergraph K and R into cliques, into copies of KQR, the complete uniform R-uniform hypergraph on Q. So in Wilson's case, it literally was decompose Kn into copies of KQ, and that designs as the hypergraph generalization. But that's not yet a matching problem. How do we make it a matching problem? Well, I invent an auxiliary hypergraph. So let F be a hypergraph, so here F would be KQR, that you want to decompose a graph, a hypergraph G, so that would be K and R, into. You can define the F design hypergraph of G as follows. It's a hypergraph whose vertices are the edges of G, and whose edges are the copies of F. Right? So the vertices are the edges, and I'll put in a hyperedge if those edges together make a copy of F. And then what's a perfect matching in a hypergraph? It's a matching that covers all the vertices. And an easy proposition is, if you had an R-uniform hypergraph, a perfect matching of that auxiliary design hypergraph is equivalent to a KQR decomposition of G. Because what would a perfect matching be? Cover all the vertices, so all the edges would be decomposed. And then to the edges, which are these copies of F, or copies of KQR. So I haven't really done anything yet. I've just explained to you you can translate designs into hypergraph matching language. But actually, essentially then what Rodel did in proving that approximate designs exist was really coming up with a strategy to prove that this design hypergraph has an almost perfect matching. And that was generalized by Pippenger and Spencer, again another famous theorem, in 1989. Pippenger and Spencer said, actually, Rodel, the thing you did, and Rodel and Frankel also knew this, but generalizes to hypergraphs. How does it generalize? It turns out that a hypergraph, as long as the degrees are roughly regular, 1 plus minus little o1 of d, and you don't have to worry about this in graphs, but in hypergraphs you have to worry about what's called codegrees, which are how many edges a pair of vertices are in. As long as the codegrees are little o of d, you can get an almost perfect matching of this regular hypergraph. And that implies Rodel's result, because it turns out this design hypergraph, what's its uniformity? Well, every clique has Q choose R edges, so it's Q choose R uniform. The degrees are all regular, because every edge, every R edge, is in exactly this many cliques. It's a highly symmetric object. And you can just check that the codegrees are this, which is little o of d. So you just apply Pippenger, Spencer, and voila, out pops Rodel's result. And I should mention that you can go beyond matchings back to edge coloring. So why can't you do edge coloring in hypergraphs? You can. And actually, they generalized it to say, if you have an R-uniform hypergraph of maximum degree d and small codegrees, you can actually edge color it with 1 plus little o1 of d. So this is the generalization of Vissing's theorem to hypergraphs, which was then further generalized by Kahn. I told you Kahn's list edge coloring. He actually proved it for hypergraphs. He proved that if you have a hypergraph, then the list chromatic index is 1 plus little o1 d. So all very nice and classical results now about edge coloring. So that was designs. Let me go to the other problem. How can you encode an edge coloring as a hypergraph matching problem? Anyone? You might say there's an obvious way to do it because, edge coloring is by definition decomposing the edges of the hypergraph into matchings. But that's not what I mean. I want the answer to be a matching, not a collection of matchings. Is there an obvious way to do that? It turns out we invent another hypergraph. So let me tell you what about bipartite hypergraphs. So a hypergraph is, how should it be defined? Bipartite, it's not clear, but here's one way to do it. We'll say a hypergraph is bipartite with parts A and B, and they're disjoint, if every edge of G contains exactly one vertex from A. So one way to generalize bipartite, it's not the only way, but one way is this. It's now asymmetric if you're gone to 3 uniformity or higher, because the A would be the special part, which only has one from each edge. But then you can define A perfect, so if you kind of know Hall's theorem and things, if it covers every vertex of A. So here's how you can translate acyclic just edge coloring into a hypergraph problem. It's via another auxiliary hypergraph. So you take a list assignment L, you define the L auxiliary hypergraph of G. I'll denote it this G bracket L. What does it do? For the vertices, I'm going to have two sets. I'm going to have the edges. That'll be my A side. And I'm going to have these weird things. What are they? They're vertex color pairs. So I'm going to put a vertex for each vertex and color. So those are the vertices. And what is that edge? Well, I'm going to put an edge as an edge color pair. What is an edge color pair? It will be the edge, and it will have the two vertices, which are the vertex colors pairs of the ends. Or if you're in a hypergraph, more generally. So here's the definition. You can read it, but that's the intuition. And the easy proposition now is an L coloring of E of G, so an L coloring of the edges of G, is equivalent to finding an E of G perfect matching in this auxiliary bipartite hypergraph. So why is that? Well, if it's E of G perfect, it means you've covered every edge with a, quote, edge color pair. So you give them the color from the edge color pair of the matching. Since it's a matching, it means that a vertex color pair won't be in two of these edge color pairs. That means exactly that it won't be, you won't have two adjacent edges. So it's a slick way. Again, I'm not doing anything hard here. It's just showing you the power of taking problems and returning them into hypergraph problems, hypergraph matching problems. Well, what's true here, it turns out as a corollary of our work, you get the following theorem. So we talked about cons, we talked about Pippenger Spencer. It turns out you can also prove a theorem for bipartite hypergraph problems. More general things are known, but with the worst bounds. But it turns out directly generalizing cons is the following. If you give me a bipartite hypergraph, and you tell me the degrees in A are at least this number, so slightly larger than D, the degrees in B are at most D, the codegrees are smallish, d to the 1 minus beta, I can always guarantee you an A perfect matching of G. So you might know this easy exercise from undergrad graph theory, right? Which is a consequence of Hall's theorem that if I give you a bipartite hypergraph, and I tell you the degrees of A are larger than the degrees of B, greater than equal D, less than or equal, you can get an A perfect matching. This generalizes, but at the cost of this little extra, little o of D factor. And that wasn't actually, I guess, known before. And it implies Kahn's theorem because of what we just talked about. You just have to check these degree conditions. It turns out the degrees of A are precisely the list sizes. The degrees of the other side are what's called the color degrees, which are, of course, at most of the degrees. Codegrees are at most 1. So we've generalized Kahn's theorem. But I want to get, that's hypergraph matchings. The talk promised avoiding forbidden submatchings. So what are submatchings and what are forbidden? Well, it turns out the two problems mentioned, high girth designs and acyclic edge coloring, can be placed in the same framework. And I've already explained this about the base problem. There's a base problem to these. There's designs and edge coloring. Forget the high girth, forget the acyclic. The base problem, I've convinced you, can be encoded as a hypergraph perfect matching problem, or bipartite perfect matching problem. So how can we encode the rest? Each problem asks for something more restrictive, high girth or acyclic. And the idea is we will encode these extra conditions as asking us to avoid certain forbidden submatchings. So a submatching is, just a small matching that lives. And it's like, I don't want my big matching to contain that small matching as a submatching. I want to avoid this. I don't want to span those. Like, somehow I want to build a matching, but no, these can't go together in it. And actually, that's exactly what you can do. So you can encode both problems as, it doesn't help us yet, but we can do this. So for high girth designs, what are the forbidden submatchings? So now recall 15 minutes ago when I told you high girth designs. Does anyone know what they are? I wanted a design that avoided these bad, dense configurations. Well, you just do that. Just the low girth configurations are sets of edges that span too few vertices. You just consider that as some forbidden submatching in the design hypergraph. What about acyclic edge coloring? Now that I've translated it as to a bipartite hypergraph matching problem, how do you make it acyclic? What do you need to forbid? Anyone? It's the bicolored cycles? Yes, right? This was what made it acyclic. And the point is the bicolored cycles is a forbidden it's a submatching. Those are edge color pairs. They're all on different edges. That's an acceptable submatching. And we're saying just forbid those. Let's just not have those. If I can then still get a perfect matching, I'll have produced for you an edge coloring that's acyclic. So that's how the two problems are related. They're both a forbidden submatching problem. Can we do anything about it? Well, so the general question is, when can we find a large matching in a hypergraph avoiding certain forbidden submatching? Very general question. This seems sort of impossible to answer in general, but can we say anything at all? And it's useful to make a definition. So we had a hypergraph G. It's useful actually to think of the forbidden submatchings as themselves another auxiliary hypergraph. So we say H is a configuration hypergraph for G if its vertices are the edges of G, and now the edges will be the forbidden submatchings. So I'll put a hyperedge on a set of matchings of size at least 2. And then we'll say a matching of G is H avoiding if it spans no edge of H. So that's precisely this forbidden submatching idea. And why is that useful? Well, matchings is a line graph problem, right? So you might know the definition of line graph. Here it is in a hypergraph. It's the same idea. It's actually a graph whose vertices are the edges, and whose edges you put just pairs. You put a pair of, an edge between two pairs, so a 2-edge, if those edges share a vertex. And the reason to view this as a hypergraph problem is, what is this problem actually asking? What you're really studying is the line graph of G, that's your matching problem, union H, your forbidden submatchings, as a hypergraph both living on the sets of edges. What you want to find is a large independent set in that hypergraph. So it's sort of this problem is equivalent to finding a lower bound on the independence number of L of G union H. So not only do you have to know about sort of edge coloring and matchings, you have to know things about independence numbers of hypergraphs, which brings us back to vertex coloring. So more generally, you could ask when you could almost decompose the edges of G into large H avoiding matchings. This, it turns out, is a coloring problem. It's equivalent to upper bounding the chromatic number of this union. And so the real question we begin to ask is the following. Under what conditions does this union have independence number, so almost the minimum of the independence number of the two, right? Because sort of you can't ask to do better than what you could do individually. So when can we hope to sort of achieve almost equality here? Or generally, same problem but in chromatic number. Under what conditions can you hope to have chromatic number sort of at most the maximum of L of G and the maximum of H? And here's our main result. So first I need some definitions. So I mentioned what codegree was. The codegree of vertices in a hypergraph is just the number of edges containing both. You can define something called the girth of a hypergraph. It's the generalization of girth in graphs. It's the length of a shortest cycle. You can debate what a cycle is. Here we mean a Burge cycle, which is basically any cycle you can think of is a Burge cycle. It's the most general definition of cycle. It's an alternating walk of vertices and edges. And I'll need, so we're going to do mixed uniformity. I need something called the I degree, which will be the number of edges of size I containing V. So far we've only done uniform hypergraphs. I'm going to introduce you to something called non-uniform hypergraphs, which have mixed uniformities. And here's our theorem. So now I'm going to state theorems. This is version 1. It's called our almost perfect matching version. It's our base version. Here's how it goes. Let G be an R uniform hypergraph whose setup is essentially Pippenger-Spencer. So the degrees are roughly regular. I'm not stating all the conditions here. There's, for all beta, blah, blah, blah. But imagine beta is your favorite fixed small number. And the codegrees are at most that. What about H? It turns out we require H to either be girth at least 5, or more generally just sort of has small codegrees. You tell me it doesn't have to be uniform, it just has to be bounded. So each edge contains at most G vertices. That's saying the forbidden submatchings of size at most G. And I need some promise about the I degrees. It turns out here, the I degrees have to be O to the D to the I minus 1, but you're even allowed, importantly, an extra log factor. And we'll get to why that is. If you have these two, basically you can get an almost perfect H-avoiding matching of G in this size. So this can sort of be thought of as a generalization of Pippenger-Spencer to this forbidden submatching land. That's the almost perfect matching version. But this, I should mention, was proved independently by that same group from before, Glakios, Kim, Lichev, and Kuhn, but only for a large D, so polylog the number, so dense, sort of dense-ish graphs. We do it in general because we use different methods. That's the base version. But we can prove coloring and list coloring versions. So same idea, as we talked about for con and things. You can prove the chromatic and list chromatic numbers are 1 plus little o1 D. So, and now I don't need it to be regular, I just need max degree D. More generally, I can show what's known as the A-perfect matching version. So that theorem I told you earlier, I'll have a bipartite hypergraph with degrees in A slightly bigger than degrees in B. Same conditions on H. I can get an H-avoiding A-perfect mapping of G. So we can get all of these, just one harder than the other, but you can sort of show how one implies the other with these various tricks. But really, this is sort of the big one. So that's our main result. And so here's the hierarchy. It's weird because at first glance you might think that that bipartite matching problem, right? In graphs, bipartite matching feels weaker than matching. But in hypergraphs, you're allowed to add uniformity. So actually, it's harder. In the way bipartite I showed you implied list edge coloring, implied edge coloring, implied almost perfect. Because like the trick is I embed the coloring as an extra uniformity. So it is actually the strongest one in our hierarchy. So it's nice to actually codify this, understand this hierarchy of problems. Because again, for us, our purposes, designs was here, but the ASIC edge colorings lived in this bipartite world. Okay, so we have all of that. What about the proof? This is my one slide about the proof. I'm not going to tell you about the proof. I will give you this nice quote. Here's a quote by Kang, Kelly, Kuhn, Mathuku, and Ostis from 2021, so before our paper. It was in their Nibble survey. So they wrote a survey of the Nibble method. They said these two threads of research, of edge coloring and of vertex coloring with the Nibble method, have developed somewhat in parallel, sometimes intertwining. And I think that's very nice. But maybe the takeaway, and you'll see in a bit, actually now they do intertwine. Our method shows you can intertwine the edge coloring and the vertex coloring via this. You can do them at the same time. So you can just prove these meta theorems that are joint generalizations. And some key ideas we had, turns out because H is allowed to have different uniformities, it's useful to track what's called a weighted degree, some kind of linear combination of the different I degrees. So I won't get into that. But the Nibble calculations for the edge side, G, and the vertex side, H, turn out they interweave perfectly, and they work together to make it work. So everything works out nicely. The paper is kind of long. Maybe it's a 20, 30-page proof even just to do it. We also needed a new version of linear talograms to concentrate, uses Lovász local limit to finish. So I won't go over the proof, but if you've seen Nibble proofs, it's a Nibble proof. But it's a hard Nibble proof. You have to make it all work together. But the point is to build these meta theorems that imply things. So really what we've done is unite two streams of research. So I know I motivated it with high girth designs and acyclic edge coloring, and we'll get back to that. It's also interesting in its own right as a question. But also, it unites two streams of research. This vertex coloring and edge coloring. Because what does our main theorem imply? So there's two questions to ask. What does our theorem imply if H has no edges? Right, you have a G and you have an H, right? Forbidden submatching is matching. What if H has no edges? So what if you forbid nothing as a submatching? In that case, it's exactly our A-perfect matching theorem from earlier. And we proved it because we wanted to prove this thing. And it turned out this already generalizes things from before. Also, you might know this by a different name. So it turns out the A-perfect matchings of bipartite hypergraph I described before is equivalent to what's known as a rainbow matching. So what you could do is you could have a hypergraph whose edges are colored, not properly, and you want to find a, quote, rainbow matching where all the colors of the matching are different. That's equivalent to the thing I said because you could just take this formulation, look at G induced on B, sort of pop out all the A edges, those become edges in B, and you view A as telling you what the color is. And then finding A perfect is finding a full rainbow matching. And so maybe now you're not surprised. Our thing implies Pippenger-Spencer. It implies Kahn's theorem. OK, more restrictive codegree assumptions, but better error terms. And what I don't have time to tell you, it also simultaneously implies a number of theorems about rainbow matchings that were new and interesting, resolving some conjectures. But I don't have time for that. But sort of that's what we've done on the edge side. What happens on the vertex side? So what if you say like L of G has no edges? What does our theorem imply? So in this case, I'm saying like, say G is a matching. So that's, the matching part isn't interesting. It's just the forbidden submatchings that are interesting. Well, it turns out there is an old theorem of Ajtai, Komlos, Pintz, Spencer, and Szemeredi from '82 that says if you have an R-uniform hypergraph of girth at least 5 and maximum degree delta, then the independence number is this number. It's V of G times log delta over delta raised to the 1 over R minus 1 root. So it turns out it's pretty easy with the local lemma to get this without the log. But if you assume the girth at least 5, no Bursch cycles of size 3 or 4, you can get this extra log factor. That was a celebrated classical result from the 80s, showing that this could be done. And there's been a whole stream of research generalizing this. So it was done for linear hypergraphs, which are girth at least 3, by Duke, Lefman, and Rodel in '95. Friese and Mubai then showed it generalizes to its coloring version. They showed you can go from linear to bounded codegree. This was Cooper and Mubai in 2016. With my postdoc, Lena Lee, just last year, we also generalized this even further to mixed uniformity. So there's some kind of take the maximum of all these numbers with a different degree, so I won't state that. Lena and I actually did it for what's called triangle-free hypergraphs, which Michelle and I's theorem does not imply, but generalizing both would have taken an extra. Lena and I's paper is like 50 pages, and ours is like 50 pages, so we didn't want to do that. But I'm saying, basically, our meta-theorem just implies all of this stream of results as well. So that's what I mean by uniting. We're uniting these vertex world and edge world into one super theorem. But to what end? What are the applications? Well, here are applications. And the point I want to get across, so do come talk to me if you have any ideas, is basically now we've built this meta theorem, and it should just be able to solve problems that are sort of the combination of a matching problem, an edge problem, and this independent set or vertex problem. So I showed you we had like these base problems, and then there was an extra restriction. If you have a problem that feels like that, it's probably because it lives in this world, and you should use our theorem or something similar to prove it. And it turns out there's many things in high girth combinatorics like that, but even other areas that don't have the word high girth in them. So I mentioned today applications to high girth designs in acyclic edge coloring. Now, so the other group also did this, but only for dense graphs and the perfect matching. But now there have been 6 or 7 papers written using these sort of black box theorems on degenerate Taran densities, generalized Ramsey numbers. Michelle and I used it to prove a conjecture of Brown, Erdős, and Schoch from 1973. So we're beginning to see these are sort of problems are everywhere. OK. So that's what I want to say about that. But let me go back to the 2 problems I said in the beginning. So I don't have a lot of time, but I have like 5 minutes. Let me show you how to prove those 2 theorems that I claimed we could do. And the point is, if you trust our big black box theorem, it's easy. It's a slide or 2. It's just checking the degrees and the codegrees. So let's just do that. I'll do it quickly. I won't do it all. So for high girth designs, again, the graph is not the graph, it's the design hypergraph. That's your base graph G. And I already mentioned that G is deregular and has small codegrees when we talked about Pippenger-Spencer, so it satisfies the Pippenger-Spencer side. The question is, what is H? So you want to forbid all of these small, low girth configurations. It turns out obviously you should only forbid the minimal ones, like inclusion y is minimal, right? And that suffices. So you do that, that's your configuration hypergraph. And what are the I degrees of h? That's the only question. We just have to calculate what are these I degrees, what are the codegrees, does it satisfy the theorem? Check. So what are the I degrees? Well, you stare at it. So in H, what's a vertex of H? Well, it's an edge of G, but G isn't G, it's this design hypergraph. So that's a clique. So it turns out what we're asking is sort of how many configurations of size I is a clique in? So how many edges of H of size I is the clique in? Well, what was an edge? You might not have forgotten, but it was this IQ minus R plus RI configuration. So it's I cliques spanning at most this number of vertices. So it means it has at most that number of vertices. So how many can a clique be in? Well, a clique is Q vertices. So I just have to choose this number minus Q other vertices. It perfectly works out to be I minus 1 times Q minus R. So what's the number? Up to constants, this is n to that number. You choose that number of vertices. Turns out this is on the order of exactly d to the I minus 1. And our theorem required d to the I minus 1, but even allowed you a log d. So here, even though the constant's large, it's going to be smaller for log d if d is large enough. And similarly, I won't do it. You can check that h has small codegrees, and small codegrees with g and things, so you just do that, but it's just calculating them out. Turns out they also satisfy it, because the problems are sort of disjoint. So our almost perfect matching theorem implied an approximate high-girth Steiner system, even a decomposition into them from our coloring version. What about the ASIC edge coloring? Same idea. What's the base hypergraph? It's this auxiliary list hypergraph. So you take a list assignment where every edge has, say, exactly that number. You consider this auxiliary hypergraph. Again, A is the edges, B are the vertex color pairs. I'll take D to be the max degree of G. What we said before was that the degrees in A are the list sizes, which is slightly larger than D. That's good. Degrees on the other side are most the degrees, so that's at most D, which is good. The codegrees are 1, so that's all fine. Same issue, what about H? Well, for H, I'm going to take all the bicolored cycles. Again, Michelle and I only did it up to a fixed length, because our theorem was for, bounded size sub-forbidden configurations. But you take the so you alternate colors C1, C2 on edges. The question is, what are the I degrees of H? Again, a simple calculation. An edge here is what was called an edge color pair. Whereas the vertex was the edge in the thing. So it's how many edges of H of size I is an edge color pair in. So how many bicolored cycles of size I is an edge with a fixed color in? You just calculate it. That size I is bicolored I cycle. So what would you do? You'd have to choose an I cycle containing the edge. And then you have to make it bicolored, so you need to choose a second color. Turns out there's delta to the I minus 2 choices of C. You choose the other vertices, right? And then there's this number of other possible colors. So you have that. What does that combine to? You product those two. You get delta to the I minus 1, which is D to the I minus 1. Again, doesn't have a log D factor, so we're fine. So there was room to spare. Again, I won't do the codegrees for you. You can just check. It works out. And so now we need the full power, because we want to get not an almost edge coloring, we want a full edge coloring. So this is where we use the A perfect matching version to get an H avoiding A perfect matching, which is exactly equivalent to an L acyclic L edge coloring of G. So that's almost my talk. I just wanted to add one addendum. So what is the addendum? Our forbidden submatching theorem implied that we can, with 1 plus little o1 delta colors, we can color that while avoiding bicolored cycles of length up to L. We did this high girth edge coloring. That wasn't the acyclic edge coloring conjecture. But you might ask, could we use this forbidden submatching framework that you've now seen as so powerful and just sort of perfectly suited to the thing, to also avoid longer bicolored cycles? It turns out the longer bicolored cycles have even lower degree in expectation. They should just be easier to avoid. The issue is, how do you prove that? How do you keep the concentrations? How do you do a matching theorem with unbounded uniformity? Seems hard. It is. But you can do it with a lot more work. So in a 70-plus page paper with Lena Lee and Michelle, a host of new ideas, but fundamentally using the submatching framework, we were able to prove the acyclic edge coloring conjecture asymptotically. So it's still not on our archive, but it's already 70 pages. We're just tidying up the proofs and calculations. But we proved that A prime of G is the most 1 plus little 1 delta of G. So it turns out first solving the L acyclic was in building this general machinery, and then we needed some more tricks. So basically we have to redo the whole proof and make it work specifically in acyclic edge coloring, but we were able to do that. So at least we've solved approximately one of the two problems I mentioned. So thank you for your attention.
Are there any questions I can ask you?
So in your main theorem, you've got this bound on the codegree and degrees and so forth. How tight are they? Like,
yeah, so we do codegrees of like d to the 1 minus beta. So you get to choose the beta, and that just weakens how good a matching you can get. That's tight with the type of concentration techniques we use. But we do get better error terms in the spirit of the better versions of Pippenger Spencer. So that would sort of be tight there. You'd need to kind of run a different nibble style proof like they do in Pippenger Spencer and Kahn. You won't get A-perfect versions, though. If you want it to be perfect, you really need more control. So you really want to assume, I think, those. They might work up to like D over polylog D, so where you can still kind of get concentration.
Yeah. Can you say something about the little order 1 term in your latest result?
Yes. So we did not try to calculate it, but it is a natural question because cons, I told you root is known. So we think if we just tracked through what happens, it would probably be something like delta over log delta. So it's not going to be poly small. We would have to do a little work to confirm that. Maybe it'd be more like log, but you'd get something out of it. It's just, yeah, delta over log is sort of not that, like it's not the right answer, right? So basically we decided maybe it's already long enough and we don't want to, but that's one of the next questions to do, try to prove the error term. But fundamentally the way we're doing it, it seems like you're not going to, without some new ideas, you won't be able to push it, to some poly root. So, good question.
Any further questions? Probably one last question we have. If not, we can do it offline. Thank you.